Hey everyone, welcome to this explainer. I am absolutely thrilled to have you here today because we are going to conquer a topic that is literally essential for your JE and NEET exams. Yup, we are talking about chemical kinetics. Now I know how tricky competitive chemistry entrance exams can be, but stick with me. By the end of our time together, you're going to have a crystal clear, highly structured understanding of how chemical reactions move, how they change, and exactly how we measure them. Let's jump right in. Okay, so let's start with a really fundamental distinction. Chemistry is all about change, right? But how we measure that change really matters. Thermodynamics tells us about the feasibility of a reaction. For instance, thermodynamic data tells us that a diamond will eventually convert into graphite. That's a pretty mind-blowing fact. But, look at a diamond ring. It's definitely not turning into pencil lead before your eyes. Why? Well, because while thermodynamics says it can happen, chemical kinetics tells us the speed of the reaction. And for diamonds, the conversion rate is so incredibly imperceptibly slow that most people think diamonds are forever. Kinetics is the study of that reaction rate and the specific conditions that control it. So here's our roadmap for today. We're going to cover fast versus slow reactions, contrast average with instantaneous rates, navigate what I call the stoichiometric trap, decipher rate laws, and then we'll finish strong with gaseous reactions. All right, Section 1, Fast, Slow, and Chemical Kinetics. Basically, to truly understand chemistry, we need to know what actually controls the rate of a reaction. It all comes down to a mix of concentration, temperature, and catalysts. Okay, let's look at some data that perfectly illustrates a core rule of kinetics. Here we are tracking the hydrolysis of butyl chloride. Notice the average rate dropping over time. Right at the beginning, the rate is 1.90 times 10 to the negative 4 moles per liter per second. But as time ticks on and the concentration of our reactant drops, the reaction slows down drastically, falling all the way to 0.4 times 10 to the negative 4. See, the speed of a reaction is defined mathematically as the change in concentration over a given time interval, or delta R over delta T. As those reactants get consumed, the reaction inherently hits the brakes. Moving right along to Section 2, average versus instantaneous rates. We've seen how our rate changes over a wide time gap, but for your exams, we usually need to be way more precise. Because a reaction's rate is constantly falling as reactants are consumed, an average rate over a long period just isn't enough to predict the speed at one specific instant. To express the rate at a precise moment, we need the instantaneous rate. Mathematically, we get this when we consider the average rate at the absolute smallest possible time interval, when our dt basically approaches zero. In your formulas, this transforms the delta into a derivative, written as dr over dt. Think of it as the exact speed at an infinitesimally small slice of time. Now, to translate that somewhat scary calculus limit into a physical reality, take a look at this curve for butyl chloride. To find the instantaneous rate at exactly 600 seconds, we plot the concentration as a function of time, and then we just draw a straight tangent line that merely touches the curve at t equals 600. The slope of this specific tangent, that gives us our exact instantaneous rate. In this specific case, it's 5.12 times 10 to the negative 5 moles per liter per second. So for your exams, I want you to keep this step-by-step checklist locked in your head. First, plot the concentration versus time. Second, locate the exact specific time t requested in the problem. Third, carefully draw a tangent line at that exact point on the curve. And finally, calculate the slope of that tangent. Bam! That slope is your instantaneous rate. All right, we have arrived at Section 3, the stoichiometric coefficient trap. Please pay super close attention here, because this is one of the most common pitfalls where test takers just hemorrhage points. Let's run through a hypothetical exam scenario. We have the decomposition of hydrogen iodide. 2Hi yields H2 plus I2. Now, if the exam asks you, does the rate of disappearance of Hi equal the rate of appearance of H2? What does your gut tell you? Well, the crucial point here is that they are absolutely not equal. Think about building a bicycle, right? 2 wheels and 1 frame produce 1 bike. You're consuming wheels twice as fast as frames. Here, 2 moles of Hi decompose to produce just 1 mole of H2. Since the rate of consumption of Hi is twice the rate of formation of H2, you can't just set them equal. To balance the overall reaction rate, you absolutely must divide the rate by its respective stoichiometric coefficient. Therefore, the overall rate actually equals negative 1/2 times the change in Hi over time. Let's see how this rule applies to a much more complex equation, like this reaction between bromide and bromate ions. Look at those chunky coefficients, 5, 6, and 3. By universally dividing by these coefficients, we can securely equate the entire reaction. So, the overall rate equals negative 1/5 the change in bromide, which is also equal to positive 1/3 the change in bromine. Just remember this rule of thumb. Reactants are negative because they disappear, products are positive because they appear. Equalize them by dividing by the coefficients, and I promise you will never fall for this trap again.
Which brings us nicely to Section 4, Rate Laws and Constants. Now that we can accurately measure the rate, how do we express it mathematically based purely on the concentration of the reactants?
I want to heavily emphasize this explicit warning directly from our source material. Listen, examiners love to trick students into assuming that the exponents in a rate law perfectly match the stoichiometry coefficients from the balanced equation. Do not be fooled by this. The rate law must be determined purely through experimental data, not just theoretical reading. Let's look at this visually. In a general theoretical reaction where A moles of A react with B moles of B, your balanced equation uses A and B. But in your experimental rate law, where rate equals K times the concentration of A to the power of X times B to the power of Y, well, those exponents X and Y indicate how sensitive the rate actually is to those specific concentrations. It essentially identifies which reactant is the true limiting factor for the reaction speed. Now, X and Y might equal A and B, but they very often do not. They're strictly dictated by experiment. And in that rate law equation, you probably notice the letter K. That is your rate constant. It's the proportionality constant in the differential rate equation. It's heavily influenced by experimental conditions like temperature and the presence of a catalyst. In fact, temperature's influence is perfectly defined by the Arrhenius equation, where K equals A times E to the power of negative activation energy divided by RT. Finally, we reach Section 5, Solving Gaseous Reaction Problems. Let's look at a highly practical application that you are virtually guaranteed to see on a competitive entrance exam. So up until now, we've mostly talked about concentration in terms of moles per liter. But for a gaseous reaction at a constant temperature, concentration is directly proportional to the partial pressure of a species. So we simply shift our units. Instead of moles per liter per second, the rate is expressed as the rate of change in partial pressure, using the units atmospheres per second. For your exams, here is a brilliant, foolproof, step-by-step checklist to set up integrated rate equations for gases. Imagine gas A decomposes into gas B and gas C. First, record the initial pressure of A at time 0, let's call it pi. Second, let X atmospheres be the decrease in pressure of A at time t. Third, if 1 mole of A produces 1 mole of B and C, then B and C will each increase by X atmospheres. Finally, your total pressure PT simply equals the remaining pressure of A, which is pi minus X, plus the pressure of B, X, plus the pressure of C, X. By setting up this initial change and equilibrium framework, you can isolate X and plug it right back into your integrated rate equations. Which brings us to a final, really important thought. Once you've successfully tracked these partial pressure changes, how will you integrate them to find the true order of the reaction? Is it zero order? First order? Answering that involves integrating the differential rate equation we discussed earlier, giving you a direct mathematical bridge between your experimental data and the rate constant itself. Mastering that calculus integration is your next great challenge. Thanks so much for joining me on this explainer. Keep practicing those core concepts, drill those problems, and you are absolutely going to crush the kinetics section of your exams.